Okay, so then we get back to the main business of the Newton-Euler method. So we went through this, we touched on this in the previous class. It's just a revision that we'll have this whole bunch of definitions regarding, which is very similar to what was there in the previous class, except that now we are going joint by joint. When we did Euler-Lagrange, we are only interested in the center of mass because we wanted to write down the kinetic energy. So that was related to the velocity of the center of mass, and then we are interested in the angular moment of inertia times omega of the link. But in this case we have to explicitly involve the moment and the forces at the joints, right. And we are following this convention that when I say Fi, that is force applied by the I minus 1th link on the ith link. So if I am looking at balance on link I, then I have to consider minus Fi plus 1 and minus mu I plus 1. So this is the only thing, and then I need to write the force and moment balance equations. And so I had mentioned that you write down the force balance equation and the moment balance equations and you work it through. Okay. I want you to pay attention to this term MiG0. Okay. And right now I want to tell you is that when we actually write the equations, we do not write G0 at all in all the equations, because then the whole set of terms gets mixed up. What we do then is essentially, after we have written the equations without gravity, we just accelerate the base frame by g upward. Okay. So that will effectively give you gravity loading. So if you want to write, if you write the gravity loading term, if you want to write it from day 1, then in every time I write a force balance equation on the 6 links, you will have to incorporate that term, right. So we save on it. So finally when we do the acceleration, we just give the base frame an upward acceleration of g, okay, and then life becomes very easy. So you do not need to consider g on every link. So we will get to that explicitly later, but just keep this in mind. This is a little trick which is employed to work on this. Yeah, this is what people like Professor Saha are very good at, these little mechanics tricks here and there to simplify things. Okay. So now we are looking at rate of change of the link angular momentum. So we have to look at d by dt of I omega. Now this I is global, but I want it in the terms of I in the ith frame. So multiply by R and Ri transpose, but when I start taking the derivatives, I will get two expressions, right. I will get Ri dot, this is the invariant, next term I will get dot of this, and in the third term I will get omega I dot. Okay. Now there is this convenient way of dealing with cross products, okay, which is through this matrix, right. Are you familiar with this matrix operation? So let us look at the terms in this. So if I have this matrix multiplies a vector, then on the first row I will get this if Ri is a vector and I generate this matrix, then multiplies the z of the R vector with the y of the vector I am multiplying with, puts a minus sign, and then multiplies the y here with the z of the other vector. So that is like finding the x terms coming out of a cross product of two vectors. So this matrix is the equivalent types. So this essentially gives me a convenient way of handling this two products, and you can show that this ends up being I bar omega I dot plus omega I cross I bar omega I. Now you already know this result from your basic mechanics and your Eulerian thing. This is just a derivation of it and just shows you how it comes about when you do that step by step. So a little bit of vector manipulation. And here the second term is often called gyroscopic moment, because it comes purely because this moment of inertia of the link as the link rotates is changing in terms of the global coordinates, right. So, if I have a object like this, after some time it is turned like this. So, what was originally the moment of inertia about this axis now becomes the moment of inertia about this axis. So, this is called the gyroscopic moment, it is just a term, and again like I keep on mentioning is that it is not really needed to name these terms. You need these terms only if you are dealing with well, they all originate out of moving frames, and so when I see this you will keep remembering the statement, right. The Newton laws are valid from inertial frames. So, and none of the frames we are really looking for are inertial except the base frame, so to speak of is the definition of inertial frame. So, we have to start naming these terms which come out and look very funny, right, omega I cross I omega I. So, then there is the motor which is there. Now, this rotates with link I. So, if you take this term d by dt q I plus 1 I mi z m I plus 1. So, if you do d by dt you will get double derivative of this of q I, right, and then you will get this term. Now, this term is again you would ideally get a derivative of this and then derivative of z, right, but since this rotates with link I you can show that this simplification. So, since this is rotating with link I, then the derivative of this is given by omega I cross Zm I plus 1. So, that is all you use. So, finally, you get it down into this rather longish term, but each one of the terms is reasonably tangible, it is just long and big, and it just tells you that usually you will do it by using a computer if you are using a big thing, but for small class problems you can do it by hand. So, finally, writing that equation is very nice, but we are interested in joint torques and joint forces. So, what we do is essentially very simple. If this is a revolute joint and I want to know what is the joint torque, if this moment is being applied I just need to project this into along this axis. Okay. So, the way I project this moment along this axis is that I just take the dot product. So, then I will get the joint torque if I am interested in that. Similarly, if this is a prismatic joint, then I will take the force and I will project it along this axis. So, I will take the dot product again and I will end up with the joint force. So, this is the thing that is being stated here. And then to this you add the contribution of the inertia torque, so that you get these values for the prismatic joint and for the revolute joint. So, that gives you joint torque and the joint forces. Finally, so there are two terms here, there is PCI double dot and there is QI double dot, which are, or rather omega I dot. Okay, this is a better place. So, I am interested in omega I dot, and then in the earlier term I was interested in PC double dot, okay, to the acceleration and the velocities, the acceleration of the center of mass and the angular acceleration of the link. So, these are two terms I am interested in. So, we know that if I am looking for the angular accelerations, then I know omega is, if there is a prismatic joint, then the angular velocity of the ith link is same as that of the previous link. Otherwise, it is simply that of the previous link plus theta I dot along the z I minus 1 direction. So, this is the angular velocity. If I take the prismatic case and I differentiate, then I will get omega I dot is equal to omega I minus 1 dot, pretty much the same. For revolute joint, if you differentiate, so you get omega I minus 1 dot plus theta double dot z I minus 1, and then how do you differentiate z I minus 1? It becomes theta I dot into omega I minus 1 cross with z I minus 1. It is routine just being stated here. It is routine if you have done a course in mechanics. So, now we had defined pi dot as this term for a prismatic and this for a revolute. If you take the prismatic case, take derivatives, you will get a second derivative here, then you will get di double dot z I minus 1 this should be, and then when you take differentiation of this term I have wrong, I have to fix this. So, we have to take derivative of z I minus 1, which will be di dot omega I minus 1 cross z I minus 1. So, this double dot will be a single dot. So, I will have to get out to fix this, and then similarly here omega I dot cross with this term, and then I have to take derivative of this. Now, to do that I have to add this additional terms. So, this then can finally be rewritten in this form, which is, you are more familiar with this, 2 di dot omega I cross z I minus 1, okay, 2 omega v rel cross terms and omega cross r I plus omega cross r I minus 1 I. So, this is just systematic expansion of the terms, and you are familiar, I mean these terms, this you know is essentially a 2 omega cross v rel kind of term, this is omega squared r like term, and they all appear in the accelerations except they are done here in terms of specific angular velocities and angular accelerations. And you note that in doing this, when you write this, it is presumed, so you need omega I dot. So, this previous page you have to do first, you have to do this first, and then you can do the linear accelerations, and then for a revolute joint you can again correspondingly obtain these terms. For the revolute joint, you will not get the 2 omega cross v rel term because there is no sliding relative velocity, okay, so that is absent. So, finally you have all these expressions, and that should pretty much put you in place. So, after this we need to do forward and inverse. So, we start from the base link, we keep on marching up, calculate all the accelerations, start from the end and come down, which we will do in the next class, and we will do it through an example. So, this is the same thing in a nutshell, the final compact form, and it becomes small because of the font size, the same thing expressed in just everything patched together.